today we are going to cover Boolean algebra and logic gates. So as I mentioned before, we are living in a digital world, and because binary logic is used in all of our today's digital computers and devices, the cost of the circuits that implement it is an important factor. So finding simpler and cheaper circuit basically is going to give you huge payoffs in reducing the overall cost of the design. That's why the mathematical methods is used to simplify the circuit, and these are basically mostly on Boolean algebra. Today we're going to talk about a brief foundation in Boolean algebra that will enable you to optimize simple circuits and to understand the purpose of algorithm used by software tools to optimize complex circuits that may have millions of logic gates. We have three fundamental Boolean algebra or logical operation. These three is going to be AND, OR, and NOT. If I want to show this in like a simple way, let's consider this binary switch. We're going to use this switch to define the operation AND, OR, and NOT. Okay. So this switch, the control signal of this switch is X. It's connected to some light. And this is going to be connected to the battery. Okay. So this X is going to control the switch and going to turn on and off the light. Okay. Now let's see how we can use this binary switch to define our operation AND, OR, and NOT. So for AND operation or AND function, we can consider two switches in series. So they have two controls. We're going to have two control signal X. Let me define it as X and Y. X and Y. So our two control signals. And then we have that light. Okay. So the switch, the light is going to be on when X and Y are going to be equal to 1. So basically X, when it's equal to Y equal to 1, then you're going to have the light on. Or we can say that the output, let's say it's Z. Okay, the Z is 1 when the light is on. Only if X is equal to Y equal to 1 and Z is 0 otherwise. So that's the AND operation, AND function in logic board. Now let's see OR function. If we want to define this OR function by these switches, the switches are going to be in parallel. And then you're going to have your light. So the output is Z, the control signal is X and Y. So that's the power. This is the power supply. So now for OR function, you're going to say z is 1 if x is 1 or y is 1, because if x is 1, the current is going to flow from the upper branch, and if y is 1, then it's going to be lower branch. The current flows to z. So then z or both, in the case of both of the switches, are closed. So x is equal to 1, and z is going to be 0 otherwise. So that's the OR operation. And then let's see operation. So the NOT function, z is 1 if x is 0, and z is 0 if x is 1. So these are the three main logical operations. If you want to show it by symbol for AND gate, you show it by a capital D. So you have X and Y as your input, and the output is Z. Then you have your OR gate. You show it by this symbol. And then you have NOT gate, which you show it by this symbol. In mathematics, we show AND by just dot. Z is equal X and Y. So this is X and Y. For OR, you show it by X plus Y. So this is X or Y. And for NOT, Z is just X prime. Sometimes they show it by X bar. Okay, so this is not X. So this is the three main logical operations and the symbols. So remember these symbols. Okay, there are two ways that you can describe digital logic system. So one is truth table, and another one is Boolean expression. Okay, the truth table is basically a table of combination of the binary variables showing the relationship between the different values that the input variable can take and the rest of the operation, the output. So the truth table, when you want to show the truth table, you're gonna have two columns. So on the left side are going to be the inputs. So let's say you have AND gate. You want to draw the truth table for AND gate. Then the inputs are going to be on the left side, X and Y, and then the output is going to be on the right side, which is Z. Then you're gonna have number of rows. The number of rows is going to be 2 to the power of n, which n is the number of inputs. For here, since n is 2. So 2 to the power of 2, you have 4 rows. So it's going to be 0, 1, 2, 3. So it's going to be 0 to 3, but in decimal. But you have to write it in binary, in truth table. So 0, 1, 2, and 3. So that's the all combination that x and y can have. X can be 0 or 1, y can be 0 and 1. So you're going to have 4 cases. The output only is going to be 1 for the case, for the last case. So for the rest of the cases is going to be 0. So this is the truth table for AND. For OR and NOT also we have same, you can draw the truth table. For all the Boolean expression that you're gonna have, you can draw truth table. Okay, you're gonna see later on in the course. Now let's see the Boolean expression. So that's the second method to describe digital logic system. So instead of drawing the truth table, you can write it as a function. So f is the name of the function, and then you're gonna have inside of the parentheses, you just put it inputs, okay? So x, y, z now is going to be the input of your circuit. So input of your logic circuit. So if you have this logic circuit, you're gonna have 3 inputs, x, y, and z. Then your output is going to have this expression, x plus y, which is OR, and not, and by z, plus x prime. So that's a Boolean expression, okay? So this expression is going to be implemented in this logic circuit, and then it's going to give you the output f. There are ways that we can write down the Boolean expression from truth table, okay? Let's say you have this truth table, A, B, and C are going to be your inputs. Then you have your output F. We want to see how to get the Boolean expression from the truth table. So the inputs, the cases, since we have 3 inputs, you're gonna have 2 to the power of 3, which is 8 number of rows. So you're gonna have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 7. That's the last one. Let's say you get the output F is going to be 1 only for the third row and going to be 1 for the last row. Okay, so for these 2 cases, your F is going to be 1. So F is 1, or you can call it it's true for those 2 cases. For cases that A, for the first case, this case, A is false and B is true because it's 1, and C is false. That's for the third row. So A is false, B is true, C is false. So it's going to be 0, 1, 0, 1, 0. So that's why we get that. So how we can write it? You can write, so it's, since A is false, you get A prime. B is true, and then C is false again. So you get prime, which is not function. Then you're going to be OR function with the other row. So this row. So this row is going to be A, B, and C. Since all of them are true, so all of them are 1, 1, 1, 1. So you get A, B, C. That's a function of F. So we're going to see this in more detail later, okay? Don't get confused. So that's just to show you we can write the Boolean expression from the truth table, okay? Any question here? Yes. So we say and, we get and here. Yes, the dots are the ands. So since we say F is true, if F is 1 or true, when A and B and C, or for this case, that's why we get or here. For these two cases are going to be 1. That one or this one. That's we get the or function here. We're going to see this in more detail later. Don't worry. So this is just showing you that we can write Boolean expression from the truth table. Okay. So now let's talk about the law and rules of Boolean algebra. The first law or rule is commutative law. This law is going to tell you that if you have A, B, or together, so A or B is going to be equivalent by B or A. So these two are equivalent. For AND, we have the same rule. So A and B is going to be equivalent of B and A. That's the first law. The second law is associative law. A or B or C is going to be equivalent to A or B or C. In the circuit, you're going to see if you have B and C, or, and then you get the or with the A, this is going to be equivalent by if A and B are going to OR first, and then OR with C. So you get the same answer. It's going to be the same for AND function. A and B and C is going to be equivalent to A and B and then and C. Distributive law. So this law is going to tell you if you have A and B or C, then you can write it as A and B, then or A and C. Okay, so in the circuit, if you have, let's say, B, C, or together, and then you have and the result with A, this is going to be equivalent by, so you're gonna have B, A, then A by C, and then you get OR function. So now you can see that the first circuit only have two gates, one OR gate and one AND gate, but the second circuit, it has two AND gates and one OR gate. So two gates compared to three gates is going to be less expensive. That's why it's important how to simplify your Boolean expression to get a simpler equation. Okay, so for the OR, it's going to be the same. If you have A or B and C, you get A or B, and then you can AND it by A or C. So these two also are equivalent. Okay, so these are some of the very important law or rules of Boolean algebra. Now let's talk about the basic theorems of Boolean algebra. So these theorems are very important for you guys. Later on, you're going to use these theorems a lot in simplifying the circuits, okay? So the first theorem is going to say you, if you have x is going to OR by 0, you get x. If you have x OR by 1 is going to be 1. X and 0, it gives you 0. X and 1 is going to give you x. X OR by x by itself is going to give you x. X OR by x prime, which is the not function, is going to give you 1. Then x and by x is going to give you x. Then what else? X and x prime, which is the not function of x, is going to give you 0. And if you have x prime, you get another not function. It gives you the x, original x. If you have x plus xy. So this is very important. So x plus xy is just going to give you x. Okay, remember this. So, and then if you have x prime y, this one is going to give you x plus y. We're going to see the proof later. And what else? If you have x plus y, and then x plus z, the answer is going to be x plus yz. So the proof for x, yx plus x is x. So let's see the proof. Because x plus x, you can write it as x plus x multiplied by 1, okay? Because before I told you x and 1 is going to give you x. So this is going to give you the same x plus x. It doesn't matter if you put and 1, okay? So then I can write x plus x, and the 1 I can write, I know that x plus x naught is going to be 1, okay? I'm going to replace 1 by this guy. So I'm going to get x plus x prime instead of 1. Then if you multiply this, then you can get x by x, you get x. x by x, you get x, and then you have x multiplied by x prime, which is x. We had it x multiplied by x prime is 0. So you get x at the end. So that's just a proof how we get x. X plus x is x. And let's prove the one. So you can write x or and x is equal to x and x plus 0. You can write it 0 is x and multiplied by x prime is 0. So you just replace 0 by x multiplied by x prime multiplied by x prime, which is x multiplied by 1, since this is 1. And the answer is going to be x. Now let's talk about De Morgan's law, very useful law in logic circuits. De Morgan's law have two theorems. Theorem 1 is going to tell you if you have A and B, and then you not this, it can be equal to A prime plus B prime. Okay, so A and B not in the logic world. So if you have A and B, the answer is A and B. And then if you put the not, you get A and B not. So this gate is called, this gate is called NAND gate. So this is going to be shown in logic gates as NAND gate. So instead of putting the not separate, so that's a separate gate, it's called NAND. So NAND is basically is AND plus not. So that's NAND gate. So the answer of NAND gate is just A and B prime. So that's NAND gate. NAND of A and B, A NAND B is going to be equal to A prime or B prime. So that's the first theorem of De Morgan's law. So complement of product is equal to addition of the complements. Now the second theorem is about NOR gate. What is NOR gate? NOR gate means that if you have OR gate A, B, this is going to be A or B, and then you complement the output, you're going to get A or B prime. So these can be just drawn as a symbol as an OR gate. So they show it this way. So this is A, B, A or B gate. So this is NOR gate. So instead of just showing the OR and then complement at the end, you just put the bubble. So that's NOR gate. Okay. So now let's see theorem 2 of De Morgan's law. Theorem 2 is going to tell you if you have A, B complement, so this is NOR of A, B. A NOR B can be written as A complement B complement and each other. Okay, so it means that if you have NOR gate, so that's a NOR gate, this can be equivalent to the bubble AND gate. So this is bubbled AND. Remember, this is just to remember how you get to De Morgan's law. If you have a NOR gate, so the second theorem that you have the NOR gate, okay? Push this bubble to the front, to the input, then you're gonna have this. Push the bubble inside, and then change the OR shape to AND shape. Then you get your De Morgan's law. Because previous slide, here you have the NOR gate, and then you have bubble AND. Just to memorize it. This is a way to memorize it. And for the first theorem, you had NAND gate. If you push the bubble in, and then change the shape of your AND, you get your first theorem of De Morgan. The first theorem of De Morgan. Okay? This is just to memorizing the two De Morgan's theorem. Push the bubble in and then change the shape of the gate. Let's have some examples and use this De Morgan's law and the other theorems that I mentioned to simplify the logic function. Okay. Simplification of logic functions. So let's see. First example, x prime y prime plus x prime y plus xy prime. So let's say you have this Boolean expression and you want to simplify, okay? If you look at here, you can see that you can factorize x prime from these two first terms. So you just factorize x prime, you get y prime plus y, and then you get x y prime. So now we have y prime plus y, so this is going to be equal to 1. You get x prime plus x y prime. And now I can use the De Morgan's theorem to more simplify this. So I call this A, so x prime, I call it as A. And then I call x y prime as B. So this is A plus B using De Morgan's law, theorem 1. You get A prime multiplied by B prime, and then the whole thing is going to have a prime. And since A was x prime, then A prime is just x. So I just A prime is x, and B prime is just x y prime. So it's x y prime and then prime. So you get x multiplied by x y prime prime, and then the prime at the end. Again, I use De Morgan's law here. For this one, I use De Morgan's law too. So I get x multiplied by x prime plus y by using De Morgan's theorem. Now you get x multiplied by x prime plus x multiplied by y, and the whole thing has a complement. So x multiplied by x prime is just 0, so at the end you get x, y prime. Let's have an example. X, let's say you have x, x prime, y. So that's a simple example. So you just multiply x by x prime and then x, y. So based on the theorems before, x prime is 0. So you get x, y. That's it. That's more simplified. Why more simplified? Because in this Boolean expression, how many gates we have? But in here, we only have one gate, one AND gate. So more simplified. Less number of gates means more simplified function. Let's see another one. Let's say you have x plus y, x plus y prime. So you get xx plus xy prime or xy, xy prime, and then yy prime at the first step. So xx is just x, yy prime is just 0, yes? And then you factorize x from these three terms. You factorize x, you get 1 plus y prime. So the answer is going to be x. Okay, let's see another example. So basically here, as you mentioned on the, I think it was the first proof that I used. So x prime z and then y z. Okay, sometimes you can simplify it by seeing this by factorizing. So one way you can write, you remember that we had multiplied by 1 and then we replace 1 by x plus x prime. So I can add x plus x prime, which is basically is 1, yeah? It doesn't affect your equation. So I add x plus x prime at the end. So I get x, y plus x prime z plus x, y, z plus x prime y, z. And from these two, I'm going to factorize now x, y. So you get 1 plus z, and then from those two, I'm going to factorize x prime z from these two. So I'm going to get x prime z 1 plus y. So 1 plus something, remember, always 1 plus z is 1. So 1 or to something is going to make it 1. Okay? So here you're going to have 1 for 1 plus z and 1 for 1 plus y. So you get 1 here, you get 1 here. So you get xy plus x prime z. So it's more simplified. If you count the number of gates, is 1, 2, 3, 4, 5, and 6. So 6 gates. And here 1, 2, 3, 4. 4 gates. So it's more simplified. Sometimes you have to add or you have to multiply some terms that doesn't affect your equation, like the one that we did here, x plus x prime.